Let's start now. Yeah, okay. Yes, 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 yeah, yeah, yeah. Let me directly go to the circuit. Mm, okay, let me comparator circuit. Today I am going to discuss comparator circuit. Uh, Comparator circuit definition is as follows. Circuit which compares a signal voltage applied to one of the input of an op-amp. Op-amp has got two input terminals. For that, one of the input we are applying reference voltage, and other input we are applying uh, uh, the voltage which is analog in nature. Two inputs of op-amp are used, one with reference voltage, other with the other analog voltage, so that output produces either high or low, depending on which input is higher. For instance, to make you familiar with a comparator, it is an op-amp circuit. There is an implicit positive supply and negative supply. Here, at the input we apply two voltages. One of them I am calling as reference voltage. This we are going to decide what voltage we must apply, whether reference voltage is positive or negative. We will decide it later. This is a fixed DC voltage. And here we have another input signal that we are applying is analog voltage, which is a time varying signal. So this circuit is operated in open loop mode. As you can see here, we don't have any feedback connected from output to input. So this circuit compares, input time varying signal with reference voltage. Whenever time varying signal is greater than the reference voltage, output will be driven into the positive saturation. When the time varying signal V in, if it is less than the reference voltage, then the output is driven to the minus negative saturation. So positive saturation is which we can call as high signal, and the negative saturation can be called as low signals. Uh, if you look at this output voltage levels, plus Vsat and minus Vsat, this seems to be like a digital output, since positive saturation can be called as high level, negative saturation can be called as low level. So in a nutshell, we can call the comparator circuit as a analog to digital converter. Here we apply analog signal, time varying analog signal, and output will be either positive saturation or negative saturation. So this is an example for non-inverting comparator. Since we apply input signal to non-inverting terminal of an op-amp, reference voltage, a DC voltage, positive or negative DC voltage is applied to inverting terminal of an op-amp. Therefore, this circuit can be called as non-inverting comparator. To proceed further, that's what so far whatever I've explained, I've given in the written form here. Comparator produces output voltage which is either positive saturation voltage plus Vsat or negative saturation voltage. One more observation we have to make here is the output is not linearly proportional to the input voltage. If you look back the circuit here, the V naught is not will not vary linearly with reference to the input voltage. It's non-linear in nature. Okay, so comparator is one of the application of in open loop mode. Op-amps can be operated in open loop mode and closed loop mode. So comparator is one such application, one application of an op-amp in open loop mode. Open loop means there is no resistance connected between output back to the input. There is no feedback here. So such mode can be called as open loop mode. Comparator finds its application in different circuits, different applications such as schmitt trigger, discriminators, and voltage level indicators. capacitors and oscillators. There are many more circuits where we can use comparators. That's why comparator plays an important role. Now, types of comparators. We just understood what is comparator, and I have taken example of non-inverting comparator. Now we will proceed to understand different types of comparator and their circuit details. Comparators can be broadly classified into two types, non-inverting comparator and inverting comparator. First, let us have a look at non-inverting comparator. Uh, Basic non-inverting comparator circuit diagram is as shown here. Let us try to understand each and every element of this circuit diagram. Uh, uh, Previously, we have seen just a reference voltage, input voltage, and output voltage along with the op-amp. Now we will see other elements present in the non-inverting comparator. The reference voltage is as usual. As I told you, it is a DC voltage. It's a fixed reference voltage. This can be positive or negative voltage. There is a resistance here. This resistance is basically used to limit the current flowing through the diodes. There are two diodes incorporated here, basically to protect this op-amp. Sometimes when you apply this excess voltage, either V in or V reference, it may damage to the op-amp. So to protect the op-amp here, we use two diodes in different directions, as we can see here. So when the excess voltage is applied here, that will get drop across these diodes. These diodes acts like the clamping. So clamping in the sense, always output will be the 0.7 extra voltage will be produced here along with the input signal. So that's therefore this diodes not only protects this and produces even additional voltage as 0.7 volts. So that's why these diodes D1 and D2 used in almost all comparator circuits acts like a protective circuit. Okay, so here the difference voltage will be clamped to either plus 0.7 or minus 0.7 depending on which signal is greater, whether V in is greater or V reference is greater. Depending upon that, the difference voltage at the input of an op-amp will be clamped to either plus 0.7 or minus 0.7. So this protects op-amp from damage due to the excess input signal. In the basic comparator, as we can see, there is a resistance, as we already told, to limit the current flow to the diode, current flow into the diode, and the input is applied to the non-inverting terminal. Therefore, this comparator is called non-inverting comparator. Okay. Now let us understand the other analysis of these circuits. Let us go step by step. Now, if I assume the fixed reference voltage of 1 volt, here in this case I am assuming a fixed reference voltage of 1 volt, which is applied to the inverting input, the input with minus sign of an op-amp, and time varying input is applied to non-varying, non-inverting terminal of an op-amp. This is what you see in the circuit diagram. We will see the analyze here what happens when input is less than the V reference voltage. If you can make out from this circuit, if input voltage is less than the reference voltage, output output will be driven into the minus Vsat. How this is, we'll explain it little later. So my first step in the analysis is input. We assume here input voltage is greater. For the first case is input voltage is lesser than the reference voltage. When input voltage is lesser, the signal going to the non-inverting terminal becomes less. Reference voltage is larger. That means the signal going to inverting input terminal is higher. That means signal going to non-inverting is less and the signal going to inverting is higher. That means the output is driven into minus Vsat. Conversely, if input is greater than the reference voltage, the signal going to the non-inverting terminal will be larger. The reference voltage that goes to inverting terminal is smaller. Therefore, output will be driven into the plus Vsat. Plus Vsat is approximately equal to plus Vcc. Minus Vsat in the output is approximately equal to minus Vee. I hope you understand the analysis. So that's how output of a comparator will be driven either into the plus Vsat or minus Vsat depending upon which voltage is greater between V in and V reference. To conclude here, when V in is less than V reference, output goes to minus saturation voltage. When the input is greater, V in is greater than the V reference, V naught goes to positive saturation. And here we use resistances R values such that that will be that can be called as the resistance that minimizes the offset. Sometimes we randomly prefer this resistance values so that the offset here is minimized when the input signals are grounded. Okay, with this analysis, let me proceed further. The same thing what I explained, now it is written here. When the reference voltage is positive with reference to ground, V in is less than the case number 1 is V in is less than V reference. V in is basically sinusoidal signal. We know that for the op amp in open loop mode, we can write V naught is equal to open loop gain times the difference between the two input voltages, V2 minus V1. Here open loop gain is very high, typically of the order of 10 to the power of 5. Therefore, this gain is very high, and input is now equals to V2 is equal to input, and V1 is equal to reference voltage. Since in our case number 1 is V in is less than V reference, V in is less compared to the V reference, so so the output gain is very high, so the output cannot go to 10 to the power of 5 volts, so therefore it stays at minus Vsat. As I already told you, minus Vsat is approximately equal to minus VEE. This is case number 1. In the same circuit, if I assume input is greater than the reference voltage, in such case, same expression can be used. When input becomes greater than the reference voltage, since gain is very high, the output goes to positive saturation. It cannot go to 10 to the power of 5 times the input voltage, but instead it stays at plus Vsat, which is approximately equal to VCC. So we have seen that V naught changes from one saturation level to another whenever the V in and V reference are changed. Basically, when V in is equals to V reference, during that time the output switches from either minus Vsat to plus Vsat or plus Vsat to minus Vsat. So this is the basic non-inverting comparator. The comparator, sometimes it's also called as voltage level detector, because the desired value of reference voltage level of input can be detected from this circuit. To proceed further, now let us analyze the same analysis through the waveform. As we have mentioned that the first waveform is an input waveform, the second is going to be the output waveform. You can observe here the reference voltage is taken as 1 volt DC voltage. It's a constant voltage. V in is a sinusoidal voltage which varies with reference to time. The positive peak goes up to plus Vp and negative peak goes to minus Vp. This is V in variation, and reference voltage variation is shown as Vref, which in this case we have assumed as 1 volt. Now how do we analyze the circuit here? Now for the here from 0 to V reference, if you observe the small piece in the input waveform corresponding to this, let's see what is the output. Here we can say that input is less than the V reference in this small between 0 and Vref, since input is less than the Vref. So as we already analyzed, when input is less than the Vref, output stays at minus Vsat. When the input crosses the reference voltage for this particular piece of curve, when input is crossing the reference voltage, output stays at now positive saturation plus Vsat. And again, when the input falls below this V reference to the complete negative half cycle, the output stays at minus Vsat. And once again, when the input switches above this reference voltage, output of an op amp, output of a non-inverting comparator switches to positive saturation. So this explains the input-output waveform of non-inverting, basic non-inverting comparator. Okay, where we have taken assumed a reference voltage as plus 1 volt. see the same analysis has been explained here. When the next case is going to be when the reference voltage is negative. What happens when the reference voltage is negative? Still my input signal, time varying signal remains as sinusoidal, which is applied to the non-inverting terminal of an op amp. When reference voltage is taken as negative, again we have to go through two cases. When the input is greater than V reference, what is the output voltage? When the input is less than the reference voltage, what is the output voltage? So now for this case, when the input is greater than the reference voltage, as we can see here, since A is of the order 10 to the power of 5, V2 is equal to V in, V1 is equal to V ref. Now in this case, it's going to be negative reference voltage. So V in we assumed as greater than V reference. So when V in is greater than V reference, this voltage definitely output goes to positive saturation, that is approximately equal to plus VCC. Case number 2 is when the input is less than the V reference. In such case, output goes to minus saturation, which is approximately equal to minus V. This can be better understood with the help of the waveform shown here. And once again, the input V in is a time varying signal, but in this case we have chosen reference voltage as minus 1 volt. Minus 1 volt. Now we will see that what happens when the input is greater than the reference voltage and when the input is less than the reference voltage. So from the circuit we already studied, when the input is greater than the reference voltage, output stays at positive saturation. When the input is falling less than minus 1 volt for this particular piece of curve, output stays at minus Vsat. Similarly, when the input changes from above V reference, the output stays at positive saturation. So far we have understood two circuits, one with positive reference voltage, other with negative reference voltage. Both are studied under the basic non-inverting comparator. So basic non-inverting comparator, we can apply either positive reference voltage or negative reference voltage, and accordingly the waveforms are presented here. Next. So now we will try to understand the inverting comparator. So far we have understood the non-inverting comparator. If you understood the non-inverting comparator, understanding inverting comparator will be very easy. So you can see from the circuit, we are applying input signal to the inverting terminal. Reference voltage is applied to non-inverting terminal. And in this circuit, the reference voltage is derived from the positive and negative supply voltage. We use a potentiometer here, so the reference voltage can be positive or negative. That can be adjusted here using this potential divider arrangement shown here. And the usage of diodes is the same as in the previous circuit. This will act like a protective diodes, and these diodes can be called as clamped diodes, since the difference voltage here will be clamped to either plus 0.7 or minus 0.7, depending on the voltage V in and V reference. The output voltage once again stays at either plus Vsat or minus Vsat, depending upon the input voltage and the reference voltage. Now let us take two cases once again. This is what the inverting comparator. V reference is the voltage that is applied to non-inverting terminal, which is of plus sign. V in is the signal, time varying signal applied to inverting terminal. That's why this comparator is called inverting comparator. Now let us analyze now. What happens when input is less than the reference voltage? Let's go back to circuit and see that input is less than the reference voltage. Let's see where this input signal goes. Input signal goes to inverting input, inverting terminal. Reference voltage goes to a non-inverting terminal. When the input is less, V in is less than the reference voltage, so output will be driven. Here in this case, output will be driven into the positive saturation, because input is less, reference voltage is larger. So conversely, if input is large than the reference voltage, the output will be driven into the minus Vsat. The same is working analysis is explained here. Input is less than V reference, output goes to positive saturation equals to plus VCC. When input is greater than the reference voltage, V naught goes to minus Vsat, which is minus VEE. So this is an inverting comparator. The same is explained with the help of waveforms again here. This is time varying signal, which is V in. Reference voltage is assumed as positive, which stays above 0 and taken as 1 volt. Now we can see here when the input is less than the reference voltage. When the input is less than reference voltage, as already we have seen, output stays at plus Vsat. When the input crosses this reference voltage, output stays at minus Vsat. Once again, when input is falling below this reference voltage for this entire cycle till here, output stays at positive saturation. So this is how the circuit works. When we change the reference voltage to negative, this is the waveform for negative reference voltage. In this case, we have assumed as minus 1 volt. Again, input is a time varying signal, reference voltage is negative. Now let us analyze the case for this. When the input is now greater than the reference voltage for this entire cycle, look at the circuit. When input is greater than the reference voltage, output remains at minus Vsat, and when the input falls less than the minus 1 volt, the output stays at positive saturation. Similarly, when the input crosses minus 1 volt, output stays at minus Vsat, which is equal to minus VEE. So these are the input-output waveforms for inverting comparator with negative reference voltage. Now, the most important thing is application of comparator is zero crossing detector. This circuit detects whether input has crossed 0 or not. So that's a very simple circuit. This circuit checks whether time varying signal, whether it has crossed 0 or not. This is a time varying signal, sinusoidal signal. From positive to negative, the signal may cross 0, or from negative to positive, signal may cross 0. So that can be checked easily by observing the output in the circuit. And one more observation what we can make here is the reference voltage when you make it 0. In the previous circuits what we have seen, we have assumed the reference voltage either as plus 1 volt or minus 1 volt. In that circuit, if you make if you assume reference voltage as 0, the circuit becomes zero crossing detector. There is no much change in this zero crossing detector except making the reference voltage as 0. And once again, this is signal V in goes to inverting terminal, therefore this can be called as inverting zero crossing detector. Similarly, you can also develop a non-inverting zero crossing detector by feeding the input signal to the non-inverting terminal and making the inverting input 0. Okay. So now let us analyze this zero crossing detector with the help of input and output waveform. Observe here the input waveform. So this is again, as I told you, this input is a time varying signal, a sinusoidal signal whose positive peak is Vp and negative peak is minus Vp. You can observe here the signal crosses 0 here from while going from positive peak to negative peak, and again once again the sinusoidal crosses 0 when it is going from negative peak to positive peak. These migrations here of sinusoidal positive to negative going or negative to positive going can be seen in this output waveform here. Accordingly, when the sine is making a shift from positive peak to negative peak, the output of the zero crossing detector changes from minus Vsat to plus Vsat. Similarly, when the sinusoidal migrates from negative peak to positive peak, the output of zero crossing detector changes from plus Vsat to minus Vsat. The same thing can be analyzed from this circuit also. When the input is greater, when the input is greater than the 0 here, the reference is grounded, therefore it is 0. So So therefore, V output goes to minus Vsat. When the input is less than this reference or 0, the output goes to plus Vsat. Accordingly, we can see the output waveform here. So this is a example. This is an example of a comparator using as a zero crossing detector. The basic comparator can be used as a zero crossing detector provided that reference voltage is set to 0. The circuit diagram is already shown to you. The comparator using comparator as a zero crossing detector, and we also presented input output waveform. Analysis is when the output is driven into negative saturation, when the input signal passes through 0 in the positive direction. When the input is passing from in the going in the positive direction, output will stay in the minus Vsat, and when the input changes from positive peak to negative peak, the output switches from minus Vsat to plus Vsat. The simple analysis of zero crossing detector. Uh, uh, Today's class will end up by these two circuits. In next class, I will present you the Schmitt trigger, since the time is time up already for the next class. Uh, if you have any questions, kindly post it, email me, or you can just send an WhatsApp also. I look forward of your feedback on the yesterday's video lecture that I have uploaded in YouTube as well as BMSITEC channel. Kindly give your feedback on the quality and the recording and the teaching as well. That's all for today. Hope you enjoyed today's class on zero crossing detector and basic comparator circuit. Okay. Okay, next class we will be announcing soon in the WhatsApp.